Hello, this is Art Mazer. Today I'll be giving you a status update of what I've accomplished for the final project. As you may recall, the project's name is A Framework for Designing Recurrent Neural Networks with Applications to Dynamical Systems. Before we get into the status update, we'll go ahead and do a brief review of the proposals. Then we'll do the status update. The status update includes code, but I will not be going into details of the code. Rather, I'll be providing an outline of basic functionality. The project is to test the ability of an RNN to predict the time series of a dynamical system. Recall, an RNN is a series of cells. Each cell represents a time frame. At each time frame, we feed state inputs of the dynamical system into the RNN cell and then ask the RNN to predict the state for the next time frame. Our program uses TensorFlow to perform the RNN's training operations. More specifically, the project objectives are to create a template that a user can configure to a specific dynamical system or to set for a specific RNN design. Then we'll test the predictive performance across dynamical systems and across different RNN designs and see how well the RNN is able to predict the state at a next time frame. We'll be looking at the predictive ability for two separate cases. One, when the RNN has complete knowledge of the state at one time frame in order to make its prediction for the state at the next time frame, and one when it only has partial knowledge of the state at one time frame, and yet it's going to make a prediction of what the state will be at the next time frame. Inputs into the program for training are the training data. This comprises of a time series of states from the dynamical system. The dynamical systems that we'll be looking at include the low energy pendulum, that's a pendulum that remains close to the vertically downward position, a high energy pendulum when we allow the pendulum to swing up to a vertical position, and an arbitrary energy pendulum, one that can be in any position whatsoever. We're also going to look at the double pendulum. We do have some preliminary results. Low energy pendulum results look quite favorable. The RNN is able to make rather accurate predictions of a next state of the system for the low energy pendulum. We're able to get up to swings of around 70 degrees and still maintain high accuracy, and 70 degrees is well within the nonlinear range. The high energy pendulum, when we allow it to go to vertical, has not been so successful so far. We still have some avenues to explore with that. As the high energy pendulum is not working, the arbitrary energy pendulum is also problematic. We've looked at the double pendulum as well, and results there are not favorable. There's still a few avenues to explore. The program outputs include a parameterized RNN, that's one that's been trained, and then measurements to determine the performance on both the training data and as well as test data. In the next slide, we can see a process flow diagram as we go through different phases from the inputs to the outputs. The left-hand side, the top, you see our inputs, which allow you to set initial conditions and then generate a time series. On the bottom, you can configure the RNN with various parameters, and we'll get into those a little bit later. Then the phase right in the middle of the slide is the training the RNN. Both the time series data and the RNN come to the training phase. Then out of the training phase comes an RNN, a trained RNN, one whose parameters have been set. That along with test data go into the testing phase, And from the testing phase, you get performance measurements, and we process the results. This next slide shows the components of the program and the timeline that we set during the initial proposal. The components include a dynamical system generator, an RNN structure, RNN training protocols, testing procedure, and a process to display results. Next, we'll go ahead and review each one of these components individually and see what their current status of development is. The first component of the program that we'll look at is the dynamical system generator. We had a deadline of August 5th for that, and we've made this deadline. It's the simplest component of the entire program. There are two functions associated with that. One function defines the vector field for the ODE, and one function goes ahead and solves that ODE. You can see at the top that we're using two libraries, Numerical Python and Scientific Python. Scientific Python in particular is being used to solve the ODE through its program ODE-int. You can see under the first function, def f, y, and t, the vector field for the pendulum is being generated, and it returns derivs. Those are the components of the two-dimensional vector field. This is very simple. The one for the double pendulum is a little bit more complex. Next we go to the ODE solver. The function which incorporates that is called def generate dynamics. You input initial conditions, a time frame, and the number of steps within that time frame into that function, and you'll return at the bottom three arrays. One is X, one is Y, and one is X next. The array X represents the input, state input into each time frame of the RNN. The array Y represents the true output, or what we're hoping that the RNN will predict at each time frame. And what is X next about? We're unable to solve the RNN and parameterize it across the entire time horizon of the trajectory over which it's going to be trained. That's very long. It's going to be an RNN comprised of 100,000 to 1,000,000 cells, and you cannot train the RNN over such a large number of cells. So it has to be broken down into time chunks, and we call this function generate dynamics at each chunk, and the input steps is the number of steps within a chunk, or the number of time frames within a chunk. So in order to maintain continuity of the trajectory, we save the final output of the ODE solver and use it as an initial condition for the next chunk. The next component that we'll be looking at is the RNN structure. This will be a work in progress. We'll be changing the structure as we get results and look for improvements. We do have a structure that's working now, and I said it works quite well on the low-dimensional pendulum. That's the result of looking at previous structures that didn't work so well. So hopefully between now and August 30th, we'll be able to improve this so that it can work on the higher dimensional pendulum and possibly the double pendulum as well. We'll, of course, be showing results for all of these, whether they're favorable or not. So the RNN structure, what does it have? It has a configurable architecture. By that, I mean you're able to configure the system with parameters, and I'll go through those parameters in just a moment. And then you also have an instruction set for cellular processing. We fixed this this instruction set, but a user with knowledge could go ahead and write his own instruction set as he pleases. So what is part of our configurable architecture? Well, looking at the top right here, these parameters, that set of parameters configures the dynamical system and the ODE solver. If you look at the NODE step equals 16, the first parameter there, that gives the number of frames in each call to the ODE solver, or the time chunk. If you remember, we have this function from the previous slide, generate dynamics, and it goes ahead and solves the dynamics over one time chunk, and that time chunk is given by this an ODE step. Next we have an ODE increment. That's the time step for the ODE solver, or the time resolution over which the ODE solver is going to solve for the differential equations. This can have high resolution and can be different from the time step between between two cells in the RNN, or the time step between two time frames. So we have this parameter called delta here, which is now set at 8. It could be set at a different number, and that's the number of ODE increments in between time frames. So for the parameters set as they are, the increment between two steps for the ODE solver is 0.05 or 1/20th of a second. The delta is 8, so the time step between two time frames is then 8 times 0.05 or 4/10ths of a second. Next we have the configuration of the dynamical space, state space, where the dynamical system resides. We're basically doing this for Lagrangian dynamics, so we're calling this configuration space. N equals 1 represents a one-dimensional configuration space for the pendulum. That will be the angle of the pendulum, and N state is the Lagrangian dynamics dimension of the tangent bundle. That's the number of state variables. For the pendulum, it's 2. It's the configuration state, or theta, plus the, in addition, the velocity of the angle, or the angular velocity. Okay, next we go to the second set of parameters. There are 2 parameters there. The second set helps to configure the RNN trainer. N step is the number of training iterates in a training session, which is the same as the number of training cells in the RNN. Well, we said that there can be many of them, up to 1 million, maybe even more. We'll see what is required. N batch, at this point it's set to 1, gives the number of initial conditions in each training session. So if we set it to 1, then we're training along one trajectory only. If we set it to a number greater than 1, we're training among many trajectories. Setting it to 1 means that the neural net will be accurate for that single trajectory, but it won't be able to make predictions for trajectories outside of that training set. Setting it to a multiple number of initial conditions may or may not allow for accurate predictions of trajectories outside of the training set. We haven't looked at that yet. This third set of parameters configures the processing inputs into the RNN cells. Recall that in each time frame of the RNN, you're feeding inputs. Those inputs are used to process a prediction, which is the output. So what sort of inputs you want to feed are configurable and given by these parameters. The first one is n visible. That's the number of states that you're going to make visible to the RNN. In this case, it's set equal to 1, and we're looking at the pendulum. So only one variable is being fed into the RNN for decision making. That variable is the angle. The angular velocity is not being fed into the RNN for decision making. So when the RNN produces a prediction, it doesn't know what the angular velocity is. In addition to what's visible to the RNN, you might want to input past states or past visible states to the RNN for it to make decisions as well. So an add-on state gives the dimension of the subspace that the neural net remembers. We usually set that the same as n visible, so it will remember, in the case of the pendulum, it will remember angles from the past. And then an add-on step is the number of time frames that the neural net remembers. So it will look into its past for a number of steps given by an add-on step. Feed output equals 1. That's 1 if the output cell is fed as an input into the next cell. So if you can feed the output into the next cell, then perhaps the next cell or the neural network can learn how to correct itself. It can recognize, oh, I've made an error in my previous prediction. Now, how can I correct that error to make a better prediction for my current prediction? And the dimension of the complete input is given by n total input. Next, we're looking at n categories, and that has to do with the specific design of the RNN. If we look at neural networks in general, they're very good at categorizing information, bucketing it into different buckets. So the idea behind the RNN that I've designed is that we're going to make multiple predictions of what the next state might be. Not a single prediction, but multiple predictions. And then based upon the information that a neural network cell has, it will choose one of those it will combine the multiple predictions into a single prediction. These multiple predictions are each categories for themselves. So now we have to go into the instruction set for cellular processing. So what has to happen in order for that process, which I just described, to occur? Well, you have to first feed the inputs into the neural network cell. So we have an input series here given by x naught, and that input series consists of the past observations, the current state that you're going to feed in, and x feed, which is your prediction for where you currently are from your previous cell. You have to take those inputs and determine which category you're going to be in. X1 gives you your category, and Y naught are the predictors for each one of those categories. Then, having all those categories together, you have to amalgamate them to make a single prediction for what the next state will be. Those predictions are put into this list called output series. So once you've gone through the process, you come here and you you place the prediction into the output series, and then that prediction becomes an input into the next cell. The next components that I'm going to look for are RNN training protocols and testing procedure. We originally had an August 15th deadline set for this, and we do have training protocols and testing procedure in place. We have results from those as well, but we might be making adaptations as we go forward and see further results. I'd like to mention that in the original proposal, I had these as separate components, but they really do come together, which is why I have them on one slide here. Why is that? The training requires a benchmark for model improvement, and the benchmark is a good testing metric. So in order to understand what's going on here, we have to know a little bit about what a neural net is and how the training process proceeds. So what is a neural net? In a nutshell, it is a nested sequence of functions with a heck of a lot of parameters, and the training process fits all those parameters to the training data so that when an input is given, a correct output is executed across the training data. So what's all the code here doing? Well, it's formatting the data so that TensorFlow functions can be called, and those TensorFlow functions can go ahead and tune the parameters. In the original proposal, I did not indicate how the data will be collected. Now that I have some experience, it appears that it's necessary to create a database, not only for collecting output data, but for managing inputs as well. So how will this database be used on the input and output side? For inputs, we have to think about how the program is working. It takes several hours or potentially several hours to train a data set. So a nice way to go about this would be to have several input parameters and scenarios set all at once, and then feed these parameters into the program, which will run several training sets overnight. And then we would like to be able to review those training sets the next day. So the database would be a place where I could store a series of input parameters, and the program could go and call those input parameters from the database. Then once it's performed its training, it could go ahead and set the results back into the database. Once all the results are there, we'll be able to once again take them from the database and make plots of the results, and the plots will be the difference between the RNN predictions and the actual state variables. We'll also be able to use the database to associate particular results with the inputs that created those results. What can I say for concluding remarks? In terms of current status, we're in pretty good shape. We have a good framework. We have a time series generator. We have a configurable RNN. We have testing and training processes in place. But I do want to mention that this is an evolving framework. As we get results back, we go ahead and make adjustments. What are we looking for in the future? We're looking for a database that will assist with running and reviewing those scenarios. As I described, then we'll be able to run things continuously overnight and then look at results the next day. And what will the results be? Well, when we make our final reports, we're going to have plots of the difference between predicted and true outcomes. So that concludes my status update. Thank you very much.